thank you all for joining us. This is the third talk in our winter lecture series. We decided to do this series so that we could bring to you some of the research that we've been doing over the last couple of years. A lot of it relates to model risk management and machine learning, some interesting topics. And the previous webinars have been recorded and are on our website. So feel free to go look there if you'd like to see what we've discussed in the past. Today, I have the pleasure of having Dr. Nick Dobrinov speak with us. He's a senior scientist here at Deep Future Analytics and a PhD in economics. Nick and I have worked together for over a decade. He's got a lot of experience in all forms of modeling for lending and deposits. And in some of our recent work, Nick was looking into how to quantify model selection risk. And this fits in well with some recent work of Model Risk Managers International Association on quantifying model risk. So actually this talk is jointly sponsored by both DFA and MRMIA. So Nick, thanks. The time is yours. I will say, while Nick is talking, if you want to type questions in the chat, I can relate those to Nick. And at the end of his talk, we'll go over more questions. So we welcome all those. Thank you.
Thanks, Joe, for the introduction. Hello, everyone. Today's discussion is about model selection risk. This study started with development of a stress model that was main purpose used for CCO forecast, but it's a stress model, and the interest was how do we quantify the model selection risk in defining the reserves, because the reserve is set up based on a point estimate, and how precise are we assuming that this is our best estimate of the reserve. Okay, so okay, the slides were not moving. Model risk is a kind of broader topic of high interest in the banking industry, in the insurance industry. Actually, when we started studying this, I realized that in the insurance industry, the interest started even in the 70s and 80s, and there's some research papers there. But some of the main components that are studied are process risk. For example, what is the chance that the required reserve is going to be different from the mean required reserve that you're expecting? Parameter uncertainty, which is relatively obvious, and then modeling framework. But there is also a risk in selecting a model within the specified modeling framework. So when you select the modeling framework, within that framework, you can have multiple specifications that are possible. And it's very difficult to figure out which one is the best, because most of the banks have very limited data that covers just one recession. Some of them even barely one recession. And for you to develop a model that has a good predictive power out of sample, you need to have at least 2 recessions in sample, and ideally 1 recession out of sample to test the model. And that's not the case with most of the clients that whose data sets we've analyzed. So in that case, you end up with a lot of different possible specifications that feel relatively similarly in sample, but they may have very different paths out of sample. And the question is, what is the error in selecting one of them or an ensemble of them as a point estimate to derive the reserves? So that point estimate typically selected as one model, or it could be an ensemble model. In that specific situation, the client selected an ensemble model. But clearly that selection of the model to derive the point estimate is going to affect the loss reserve. So the objective is to quantify the model selection risk and its components. And since this was a CISO objective model, purpose for CISO, we also try to get distribution of the lifetime loss forecast as best as we can, because that in our case is not as straightforward to do. So what we have in this data set, these are mostly commercial mortgages of different varieties. We have non-owner occupied, we have CNAs, and we have some consumer mortgages. Actually, that was a relatively large portfolio in terms of different products, but for this study we selected 3 of them where we had more data. And clearly we want to develop a stress model, but we don't have enough data. The data is very sparse. You can see how noisy the probability of default is. So we had to select to develop a relatively simple model. And in that case, that was just a macroeconomic model on the probability of default without measuring any life cycles or loan or borrower characteristics affecting the measured in the model. And so we have relatively parsimonious models. We don't want to overfit the noise in these curves. And we have numerous factors that are affecting the portfolio, but the models are parsimonious. We select maximum 3 variable models. And so one of these models, so 2 to 4 models can be entered into ensemble. They will get the point estimate that will be used to derive the reserve. And then there's a large universe of models that are basically not used. And some of them obviously will have lower performance. The performance will deteriorate pretty fast, maybe after the first 20 or 30 models. You're not going to be as interested in those models that have lower performance, but still there are a lot of models that have very similar performance, and their predictions will diverge out of sample, which is going to drive a model selection risk in that situation. Again, we selected the better populated sub-portfolios from this portfolio. We have CX construction and non-owner occupied and some personal mortgages. The default rate is very low, so we have, and this is quarterly data, so we have very few defaults per quarter. We have a lot of zeros in the probability of default for each of these segments. So we use the binomial fit to fit the models, basically with the logit link. For the macroeconomic indices that we use, we specify the expected sign and impose the expected sign. So we don't allow models with a sign that's not as expected. And we use transformations that are stationary. So if a variable like GDP or some form of measure of income is unbounded and it's growing in one direction, it's moving in one direction, then we only allow rate of change transformations for such a variable so that we have at least theoretically stationary predictors. For variables that are bounded like unemployment rate, for example, we can also allow moving average transformation. Which we believe is stationary. We're also interested, as everybody else, in the lag of how the macroeconomic shocks are propagating into your portfolio defaults. And apart from the lag, we know that there is going to be a range of effects here after the initial shock, because you have a lot of different consumers that have different risk characteristics. Some of them are in better shape. They're going to be able to pay longer. So that naturally will lead to a need to use something like a distributed lag model, but that in itself is going to require a lot of parameters. So we place some structure in these parameters by defining a window, and the window is basically going to be the span over which a certain transformation is produced. For example, if it's a 12-month window for a difference transform, that is a year-over-year change. So it's something typical that a lot of the institutions are doing, placing some structure on this distributed lag model to estimate field parameters and still capture this varying timing of response to an economic shock for different consumers, different borrowers. We constrain the lag to maximum of 2 quarters and the window to maximum of six quarters, which is 18 months. We're targeting basically quick response to a macroeconomic shock. And the window up to 18 months, that comes from experience with a lot of portfolios, producing a lot of models for regulatory purposes, and just discussing this with regulators and internally. So the model selection, we have a few different criteria. We apply them as filters. We optimize on lag and window, rank models by AIC. The residuals by expectation always serially correlated. So we always use New West p-values. The signs have to align with business intuition. VIF is kind of a moving target. If we have a lot of models, we really narrow it down. We also really interested in how well the model is stressing. So we can have models that explode in terms of stress and models that provide too little stress. And we're looking for models that will provide stress that's commensurate with previous recession levels. And after these filters are applied, the models are manually reviewed by the management team. So let's say now we have 50 models. Management team is going to review the models for the indicators that are included in the models, the stress that it's producing, and they're going to narrow down to, let's say, top 3 or 4 models. In that case, the client selected to use an ensemble model that was equal combination of 2 to 4 models. So this is the model development basically. It's relatively standard type of filters and considerations that would be applied in a CCAR model or CISL model. So for the next of the study, we will try to compare the best TIC model when these filters are applied, the ensemble model that was selected by the client, and the next best 30 models by AIC that are not including the ensemble of the best AIC. So again, we have only one recession in the development sample, no recession out of sample. So statistically, that's not a well-specified problem. We expect a lot of divergences in the paths of these different specifications out of time. And on these first plots here, you can see the best model is the red line, and the ensemble model is the green line. So between the red line and the green line, this right now is in log odds space because we use the binomial fit. In log odds space, we see a variation between -5.8 to -6.2, -6.3 between the best TIC and ensemble over here. In terms of probability of default, this is about 50 to 60% spread between the two. And when you plot the variation in the next 30 models, you can see that in log odds, this is between minus 5.5 down to minus 6.7. So this range here at the widest part is leading to a spread in probability of default around 75 to 90%. And it narrows down later. And this spread, interestingly, is narrower for the severe scenarios, as you can see here. It's something that it's probably a subject of another study, why that is happening. That's for the future. And this here is CI construction loans. This is for non-owner occupied. We see similar variation. And this is for consumer mortgages. Now you can see there's a lot of gaps in this data. We don't have points here, which means defaults were 0, basically. Okay, so in the next part, we want to see how the prediction interval for the best model, best AC and ensemble model, compared to the variation that we see in the next 30 best models. And since we have a logistic regression model, most of you that work with logistic regression know that the errors in logistic regression are not well defined, and it's not straightforward to define what the prediction interval is for a logistic regression in probability space. There is no straight answers. There are people that have tried to approximate ways to approximate it, but there is no clear answer to that. So we, for the most part of this study, we work in the log odds space because the residuals there are close to normally distributed, so it's easier to get an answer there. And the prediction interval in log odds space is going to be composed of confidence interval and mean squared error. Right, so we approximate the mean squared error by the mean squared error in the log odds space. And for this study, we work with 2 standard deviations for the confidence interval and the prediction interval. And just as a quick reminder, the difference between the confidence interval and the prediction interval is that the confidence interval will measure how well your model is predicting the mean. So you're going to get, the confidence interval is going to be relatively narrow, right? It's the error in predicting the mean. Well, the prediction interval is going to measure what are the possibilities for a point appearing in a certain range. Let's say with 95% probability, we can say this is the range where the next point is going to appear. That could be far away, very far away from the mean. So these are all the possibilities, and they come with some distribution. Right? In log odds space, that will be a normal distribution. The prediction interval is going to combine the confidence intervals on the estimated mean and the error in the model. So for the ensemble models, for us to get a prediction interval, we need to combine the confidence interval somehow. And that's not just adding them together, because we're basically looking at the variance of one confidence interval plus the variance of the other confidence interval. So their relationship, their correlation is going to be used in estimating what is the confidence interval for the ensemble model. So to do this, we measure the correlation between the residuals of the ensemble models. In our case, we only have 2 models in each of the ensembles. For this specific sub-portfolios that we are presenting here, but some of the other ones had more than 2 models. And we see that the correlation between the residuals within the ensemble, between the 2 models in ensemble, is 0.9, 0.7, 0.74. So it's relatively high. And that formula here is going to give us the prediction interval for the ensemble model. Now, when you look at the next best 30 models and you try to derive a confidence interval for those 30 models, we found mathematically that confidence, that portion of the prediction interval that's coming from the confidence interval is going to grow with minimum square root of n. And that's relatively easy to see if we assume that these 30 models have uncorrelated errors, and just do the math, and we'll see that prediction interval is going to explode. If we were to just bring the next 100 models, our prediction interval is going to be explode, and it's going to be uncomparable to the ensemble that we used in deriving the reserve. So for that reason, just to stabilize the uncertainty, we replace the confidence interval part with the standard deviation between the 30 models at each t. And the next plots are going to present now the best AIC and ensemble models and their prediction intervals, which are the red and green. The large blue intervals here are the prediction errors of the next 30 models. If we were to use the confidence intervals of each of them and put them into an ensemble, our prediction intervals are going to be very, very wide. If instead we don't use confidence intervals and we use the standard deviation between the 30 models, that will be the purple line and purple bars. They're going to be very similar to the prediction interval in just one model or the ensemble models. So if we were to take these 30 models, use their standard deviation, we're going to get a very similar spread comparable to the prediction interval of a single model. And as you can see, this spread is relatively equal in size for different t. The reason for that very likely is because for small n, that spread is overwhelmed by the root mean squared error, not as much by the confidence interval. Confidence intervals is going to be relatively close here. It's still visible, but it's relatively narrow. So the same thing we see for non-owner occupied, base and severe, and then for mortgage loans. So all this work is done here in log space. For the next step, we want to see can we get some idea of this error for cumulative probability of default. We didn't have balances for this portfolio. They were not provided by the client. So instead of accumulating balances, we're accumulating the probability of default. And our model is modeling a probability of default that is default accounts divided by active accounts in the previous period. So the probability of default that we've calculated is conditional on the surviving active accounts. For us to do the cumulative probability of default, we first have to transform it into unconditional probability of default. And this is the formula here. We see that we basically have to multiply probability of default distributions here to get to the unconditional probability of default. And we also, to do this calculation, to calculate the surviving active accounts in the next period, we're using probability of attrition that was provided by the client as a historic average. So that is fixed. It doesn't vary by time. And the lifetime probability of default is just an accumulation of these unconditional probabilities. Again, there is no clear definition of what a prediction interval is in probability space for the logit model. We know that the density function for the probability of default is going to be logit normal, and basically that is its equation. So in log space, the distribution is normal. In probability space, it's logit normal. For us to get prediction intervals for unconditional probability and lifetime probability, we basically have to multiply logit normal distributions. So getting an idea or calculation of this in probability space is kind of beyond the scope of this study, because that's a totally different area of research to get what is the distribution of multiplying these probability of defaults to get the unconditional probabilities. So for that reason, our approximation to that problem is to run simulations in log space, Monte Carlo simulations for each t. We produce 10,000 samples, where the mean for each t is the model forecast. So that's the mean that's predicted in log space, and the standard deviation is going to be based on the prediction interval. So far we used prediction interval for, say, 2 standard deviations. In that case, we just divide it by 2. We create 10,000 samples for each t, and then these 10,000 samples are going to produce 10,000 different paths for the probability of default in log space, or for the log odds, basically. For the next best 30 models, the prediction interval again is going to be based on just the standard deviation between these 30 models for each t, just to keep this variability kind of in check so it doesn't explode. And again, we don't have balances, so that calculation is only going to be done for cumulative probability of default. And once we convert everything, all these 10,000 paths into probability space, we want to look at the percentiles for this lifetime PG distribution. The lifetime for these products was relatively short, 3, 5, and 6 years. That was provided also by the client, and that's what we use for the calculations. And this gives us a tabulated view of some of the percentiles for cumulative probability of default. This will be the forecast of either the best model, the ensemble model, or the ensemble of the next 30. So it will be the point estimate of the forecast. From the 10,000 Monte Carlo simulations, we're getting this distribution in its percentiles. And that's done for all 3 products. It's also done for severe scenario. And the first thing that you see that's very interesting is that our point estimates for the cumulative probability of default are systematically lower than the median of this distribution that we derived through Monte Carlo simulation. So when you're converting a model from, I guess when you're converting the normal distribution from log space into probability space, in probability space, the logit normal distribution is actually not symmetric. For lower probability of default is skewed to the right, and for larger probability of default, let's say close to 1, is skewed to the left. it's skewed to the left for low probability of default, skewed to the right for high probability of default. So we suspect this is one reason why you're getting, when you have very low probability of default, that median is kind of away from these low levels to the right, so it's kind of higher. But we haven't obviously used other data sets to see that this result will be repeated there. We don't clearly understand the relationship between a single point estimate and what happens when you're accumulating probability of default for a lifetime, what happens to that distribution, how it relates to a single point. So we cannot say that you will always get a point forecast that is lower than the median of this distribution. But that has to be checked for your specific portfolio and your specific problem. And clearly, when you're setting up the reserves have to be close to the median of this distribution, right? Because otherwise, in our case, they appear to be underpredicted. And you're trying to get your best estimate to set up the reserve. So you should be closer to the median. Then the next part of this is that the distribution that we derived for the cumulative probability of default can be used, the percentiles of this distribution can be used to calculate the economic capital, because the capital calculation is now using uncertainty more than the calculation of the reserve. So this is one way to kind of get a good idea of what the uncertainty in the selection of the model is going to be and how it's going to affect your capital calculation. So the main conclusions, three, the loss reserve needs to be increased if it's under predicting the median of this distribution for the cumulative probability of default. Second thing is the uncertainty captured by this confidence interval on the cumulative probability should be used in calculating the economic capital. And the last, I think, very important observation is that even if you just select one model and you propagate the model through all the work that we did here to derive the prediction intervals and get this 95% confidence interval for lifetime probability of default, that will give you a close enough answer to what you're going to get from calculating the variation in the next 30 models. So just propagating the one single model, the ensemble of models that you get through calculating prediction intervals and the confidence interval for the cumulative probability of default will give you a close enough answer. Because if you look at this table, the forecasts are relatively close, the intervals are relatively close. Obviously, when we're using the standard deviation between the next 30 to derive the prediction intervals in log space, not when we are using the real confidence intervals there. So these are the findings of the study so far, and again, just based on this single data set of three sub-portfolios.
Thank you, Nick. That's great. I have received a few questions, and I kind of ordered them here, not by the order I got them, but just to cover a range of topics. So one question is just from the project you did here, should we always just use an ensemble model? I know that you spent a lot of time going through the model selection process, and I guess the question would be, was it worth it, or should you just use those top 30, basically top end models, and forget about model selection?
Yeah, I kind of find this as, with my work with clients, I find this as an internal preference, a kind of management preference. Still see clients take one model, select just one model, some of them select ensemble model, but it's really an internal preference. If you look at this table, right, then to get the reserve, I guess you can take the next 30, right? Instead of going through so much work, because that process from top 30 to top 3 is the one that takes a lot of time, right? It's very inefficient process. It takes a lot of internal discussions, and quite a ton of time. But just taking the top 30 will give you a very similar answer from what we're seeing here.
And perhaps that's because of the filtering process you go through to get even to the top 30.
Yes, our filtering process is very strict. So for some of the segments, we didn't have even 30 models where the data was very thin. We had 7 models that are passing all the filters. So the uncertainty there is pretty high. In that situation, how can I say, well, that one single model is going to be the model I will use to predict my reserve? It becomes more shaky. For other portfolios where you have more data, obviously, you can have far more opportunities or far more alternatives to work with. But the filters are relatively strict.
Oh, sorry.
Go ahead.
Yeah. We have another question about have you back tested the methods to set intervals against the Great Recession to assess whether they captured the range of the actuals? Do you want to speak to that?
No, we have not tested that.
The Great Recession, the 2009 recession, was actually in your in-sample training, right?
It's in sample, yes.
Yeah. So it's not, what you're saying is it's not a back test. You didn't train the model without that and then try to test it because
No.
you wouldn't have any signal to train against in that case.
No, you will have nothing, basically, in that specific data set, right?
Right.
Some data sets very rarely would go to the early 2000s. Maybe you can do something with that data, but with this specific data set, we were basically barely kind of scraping data to get any models out. It was pretty difficult.
And another question, would your results change for other model types? So you were doing time series models. Do you want to speculate on other model selection, whether it's scoring or something else?
So for scoring, my personal experience, and Joy, you also have a lot of experience, but my personal experience is that you don't really have such a large variation in factors that you can be using before they actually start replacing each other, right? So if you're using some form of credit score, that will represent a lot of the information that you have in other variables. So I'm not sure if we're going to get, even let's say we replace FICO score with delinquency, some measure of delinquency that's going to be very predictive. Are we going to get that much variation in the outcomes out of sample?
I'd say in a behavior scoring context, you'll get more collinearity between variables.
That's what I'm saying.
Yeah, And so if you use some kind of a principal component analysis or something to combine effects, that, that's one way of solving it. If you went through model selection and kicked out correlated variables, you could wind up with a set of different models, which you wouldn't have to do the propagation of error because it's a single time step essentially, but you could do that same kind of comparison of means and distributions between the errors, right?
Yeah, and they will start converging quicker, right? Because your effects are going to get attenuated pretty quickly, right?
Yeah.
So you're not going to
And
get
then,
that much spread towards, let's say, 2 years from now.
and then there's a question here, going back to that speculation about when you were testing the models with a severe scenario and the deviation looked more narrow. It says, could the spread be narrower in the recession because you selected models by fitting a recession? Basically, do the models line up under a recession scenario because that's exactly what you trained them for?
Well, you don't train only on a recession, correct? My personal hypothesis is that, but I don't have experience in that, but my personal hypothesis is that recessionary scenarios are likely more correlated than base scenarios, right? Because imagine what happens in the economy when you have a spike in volatility, right? Let's say you have a very large spike of volatility in the stock market. Then everything starts moving in the same direction, right? So in a recession, this correlation matrix between all these macroeconomic indices is going to be kind of tighter. They're going to be more correlated. And that's my speculation, is that that's what you get in the out of sample predictions. That's part of it is coming from there. But it could be that just training on the last recession is important as well. Though we're not just training on the recession, because one of the filters that I didn't put in the slides is that we want to make sure that we are fitting the recession well, but we also want to make sure that the model is fitting the recent history very well. Because if we have a discontinuity in the recent history, then that's just a recession model, right? I don't expect to get a base projection that is reasonable in that case. So we don't really just fit the recession. We focus on both recessionary and non-recessionary periods equally.
Okay, that's great. That looks like it covers the questions we've gotten, and I appreciate those questions.
Thank you.
Thank you, Nick, for the presentation. This was great. And we do have another one. I don't want to jump away too soon because we have a few minutes. So there's a question on stationary. Let's say the input variables are not stationary, but the model developers use NUI West to obtain confidence on the estimators. Is that sufficient in the context of this testing? Is there an issue there?
So typically in these models, we do transformation of the independent variables that is stationary, right? At least expected to be stationary. You have to have a very long series to really be able to test this. And typically our residuals of such models will be stationary. So we've done this for many models. So the residuals usually come out to be stationary, even though the dependent variable very usually also turns out stationary, even though we don't have very long time series. So in terms of
So
in terms of are those, is there any concern with spurious correlations here? The answer is most likely no. No. Right.
yeah, so the reason we use the Nui West p-value estimation is for serial correlation of errors, right? Rather than non-stationarity.
Correct. Because the serial correlation is going to attenuate the covariance, the variances of the coefficients. And so the inference based on the normal variances, the OLS variance is incorrect.
Yeah, and we leave that serial correlation in the residuals of these time series models.
Yes.
Yeah, because the the standard statistician approach to put in a moving average term on the errors, an MA term, runs the risk of reducing our correlation to economic factors, and we want to leave the purity of the model of just using economic factors and let the Nui West estimate take care of the rest.
Yeah, it reduces the sensitivity. How many times we have tested moving average in the residuals, and it always reduces the sensitivity to the macroeconomic factors. So that's why we, instead of doing this, we just use Nui West variances to run the inference analysis.
Mm-hmm. And another question, I was wondering if the PD forecast range for the severe scenario is narrower than base, just because you plot it in log odds scale. When probably plotting in probability scale, would the range be more comparable? It's an interesting observation.
That's an interesting thing to test.
I don't think I know that answer either.
Yeah, we need to just calculate it.
I would say from the math, the models entirely fit in log odds space. So intuition is that it shouldn't be, but that doesn't mean it isn't. Okay. Well, then I will, I'll say last call. Any last questions? This has been great. I appreciate the interaction of our group assembled here today.
Yeah, thank you everyone.
All right. Thank you, Nick. And thanks everyone for joining.